So now let's talk about some practical applications of exponential functions. This one you may have seen before. It's the simple interest formula, and the different variables that we have here. P stands for the principal, and that is not Mr. Waldman, but that is the amount of money or the amount of value that you start off with. R is the rate. T is the time, and that's measured in years mostly. And then there's one thing that you need to watch out for. In your formula you have a plus minus, and what that means is that you can use the formula with 1 plus r or 1 minus r. If you have 1 plus r, that means that you're going to be talking about growth, about the value growing. And if you have 1 minus r, the value of your object is going to go down. It's decaying. Okay, and here's our example. You buy a new car for $24,000. The value of the car decreases, so goes down by 16% each year. Write an exponential decay model for the value of the car after 2 years. And A stands for the amount really, and that is what we're trying to find out. So the amount or the value of the car after 2 years is going to be $24,000, which was the beginning, times 1 minus r, and the rate, when we do that, we always have to show it as a decimal, not a percent, so it's 0.16, and that all that gets raised to the power of 2, because t, our time, is 2 years. And for that type of math, we can of course use our calculator and plug it in. So 24,000 times, and now use parentheses always, 1 minus 0.16, and that gets raised to the power of 2. Enter, and you get 16,934.4, or in other words, $16,934.40. So that's the value of your car after only 2 years. The car that you paid $24,000 for after only 2 years is worth only $16,000. Lost a lot of money in the deal. Okay, on to our next example, and the next formula is related to the one above. It's a little bit more involved, and this is the compound interest formula. This is when interest gets compounded. In other words, interest that you already earned earns money again. And you have one more variable to pay attention to here. It's n, and n is the number of times that you are compounding in a year. Remember, t is counted in years, so n is the periods inside of a year that you are compounding. Okay, and here goes our example. You deposit $1,000 in an account that pays 8% annual interest, so per year. Find the balance after 3 years if the interest is compounded with the given frequency. We have two different ways here. We have quarterly compounding and monthly. So for our quarterly compounding, n is equal to 4. We do that 4 times a year. We do it every quarter. So the amount that we're going to end up with is equal to the $1,000 that we had in the beginning times 1. And is the money going up? You are earning interest, right? So it's plus the rate, which is 0.08, and that divided by 4, and then it's going to be raised by the number of years, 3 years, times the number of periods for each year. 3 times 4, that's 12. Now that one we're definitely going to do on the calculator again. So 1,000 times, open parentheses, 1 plus 0.08 divided by 4. And here you don't need parentheses because division will be done first anyway. Close your parentheses now, and that we raise to the power of 4 times 3, or 12. Enter, and we get $1,268.24. $1,268.24. Now let's see how much we get if we compound monthly. And if we compound monthly, that means that n is equal to 12, right? So our amount is going to be $1,000 times 1 plus same interest rate for each year, but divided by 12, and then 3 times 12. And here goes our calculator. 1,000 times 1 plus 0.08 divided by 12, and that gets raised to the power of 36. $1,270.23. $1,270.24 actually. So we do get a little more money. It's not a lot, but it's like $2 more for compounding more frequently. That's interesting. Keep that in mind. Now we could just keep going, and we could make the number of periods that we're compounding and larger and larger, and then we would probably get more money in each case. Now we could take this all the way to infinity, but then we would reach a point where this whole expression will become the number e. The number e is an irrational number, and it's 2.718, and that number is a very important number. It is called Euler's number after the mathematician Euler. It's also called the natural base. So if this whole thing gets replaced by e, then our formula, and this is the formula for the continuously compounded interest, continuously compounded interest becomes a is equal to PERT, or at least that's the way to remember it, P times e to the power of RT. And now we're going to see what that's going to do to our money. You deposit $1,200 in an account that pays 5% of annual interest. After 10 years, you withdraw the money, and you want to know how much it is. Find the balance if the interest was compounded quarterly, and find the balance if the interest was compounded continuously. A is equal to 1,200 times, we have to use our formula from before, 1 plus 0.05 divided by 4. Quarterly means 4 times a year, and that gets raised to the number of years, 10 times 4. And so that will be 1,200 times 1 plus 0.05 divided by 4 to the power of 40. And we get $1,972.34. Alright, so far so good. And how much money do we get if it gets compounded continuously? So we're taking the other formula now. A is equal to the principal 1,200 times E, which is Euler's number, to the power of R, the rate 0.05 times 10. Okay, then 1,200 times. Now, where do we find our Euler's number on the calculator? We press second and go down to ln, and there it is. And the fact that you can find this on the calculator itself already shows you that it's a quite important number, similar to pi. So that is to the power of 0.05 times 10. And let's see what we get. We get $1,978.47. So it is again a little bit more, but this is how far it goes. You can't go beyond that amount. That is the maximum money you can earn for just increasing the periods of compounding your interest. All right, that's it for today, and I will see you in class.